Yeah, all right. Thank you so much for the introduction. And my name is Chen, and today I'm going to introduce our work on deformable motion simulation in soft tissue cone beam CT with learned models. So this work is part of the iStar lab at Hopkins. We appreciate the collaborations from our collaborators as well as the funding support. So as you see in the previous presentation, motion is a challenging topic in cone beam CT. So here we see some conventional methods on motion compensation, where these methods using metrics purely based on image properties, for example, image sharpness or piecewise constant image, which can use for rigid and deformable motion compensation. There are also metrics for some more specific tasks, for example, vascular imaging. However, these metrics sometimes might not have an accurate representation of the anatomy underlying. So which in case, image might look good to the metric, but not actually looking good in reality. So current trend on using learning-based methods has actually started to incorporate the learned features from the motion track data to reduce the chance of unrealistic solutions. As you just heard about, right, my colleague presented his work on a deep autofocus method on deformable motion compensation, where there are also works using appearance learning, which added the which used to predict the reprojection error and added to the learning, as well as some works address this problem by directly learning the motion trajectory by using the end-to-end learning. So all these learning-based methods, they actually requires large amounts of training data. So one example on the right, which actually shows one example of this supervised training setup. And here it requires known motion as a reference. However, current available clinical data does not have the motion information in general, which might not working for this. So people are now training their approaches using the simulation data. It is actually very hard to model the motion because it has a complex nature and can vary from, for example, rigid in brain imaging or to deformable soft tissue motion in the abdominal imaging. The motion can also comes from a complex combination of different sources. For example, motion can happen in the static regions combined with highly distorted regions, as well as the motion can be periodic or aperiodic, which can also mix with different motion frequencies. So therefore, we argue that there's a need for realistic stochastic motion simulation to capture the complex nature of motion, which being presented in the clinical data. And here are some strategies for the motion simulation. So first, it might not be ideal to use the only handcrafted features, as most of these approaches using simplified patient motion, which may result in unrealistic motion patterns. So we ask, can we learn the motion directly from the clinical data, which allows for the simulation of random and realistic motion? There have been some works presented on this topic. For example, there's one about simulating periodic respiratory motion in XCAD imaging with some very interesting results. But this method actually does require 4D patient CT as a reference, which is not usually the case for the interventional imaging. So we hypothesized that a synthesis model based on generative adversarial networks can be used to learn the motion characteristics which are presented in unpaired motion corrected clinical data. And the scope of this work is a proof of concept study, which we studied on highly controlled simulation cases with known motion fields. And these known motion fields will allow the validation on the motion patterns which being generated from our model and to demonstrate our solutions potential moving forward to clinical cases. And here is an overview of our network, and it has two parts, the motion synthesis part and the adversarial training. So let me start from the left part, the motion synthesis. So here, static cone beam CT projections are divided into a set of consecutive projection views, and these projection views are being reconstructed to partial angle reconstructions, which is the concept you just heard about, using FBP. These static partial angle reconstructions are then feed into our generator model together with a random perturbation, which outputs four-dimensional motion vector fields in B-spline basis. These sparse motion vector fields are then being interpolated and used by the spatial transformer to apply deformation on the static partial angle reconstructions. So here we can get synthesized motion traffic cone beam CT data. Another part of the framework is the edible stereo training, where we have the motion traffic cone beam CT projections, and we reconstruct it into the motion corrupted cone beam CT data. A discriminator model is introduced here, which helps to enforce realistic simulations from our left branch. And again, our whole setup is differentiable, so we can backpropagate the gradient for the learning-based optimization. So we can look at closer at the structures of our motion synthesis model. For the generator, our generator has a 3D unit structure with the encoder and decoder branches. The encoder branches actually extracts the features from the static partial angle reconstructions into feature maps. And here, a random perturbation which captures the randomness of the motion is being added and entered together into the decoder branch. We also apply this generator in a backward direction, which there's no random perturbation is added to enforce the cycle consistency on the static image domain. Again, our unit model is not a typical image-to-image translation model, but actually our output is a motion vector fields in B-spline coefficients. And here are some details of our adversarial training. So our discriminator model actually features a cascade of convolutional layer, nonlinear activation, fully connected layer, and the sigmoid function. So the discriminator is trained to justify whether the input image is coming from the real domain or from the synthesized domain. It is worth to mention as well that our model is trained in an unsupervised fashion, and our training data are not paired. And here we present some loss metrics on jointly training our model. For the generator loss, we apply several objectives, both on the image domain and on the motion vector fields domain. So on the image domain, the synthesized motion image is judged by our discriminator to enforce the realistic motion simulation. On the other hand, there's a cycle consistency loss, which we use the L1 norm to enforce the cycle consistency on the static image domain. On the motion vector fields domain, there's a variety penalty, which actually promotes the variability in the output as a function of the distance between the latent perturbations, which in other words, this penalty actually penalizes our generator when the output motion vector fields are not randomized. And finally, there's a smooth penalty, which actually which helps to penalize unrealistically large or like abrupt motion. So in total, these four, sorry for this. So yeah, in total, these four losses are being weighted and added together as our total generator loss. For the discriminator loss, similarly, a typical GAN loss using the mean square error was introduced to justify the input image domain. And here we introduce the validation of our method. We designed to train the network in a control scenario so we can validate our model's performance. For the training data generation, 68 MD-CT scans from the cancer imaging archives are selected. And here, the cone beam CT projections were generated by the forward projection using a high fidelity simulator we have with C-arm geometry as shown here. Here, a set of 12 partial angle reconstructions were generated where each of it contains the back projection from the 30 consecutive projection views out of in total of 360. Our motion corrected training data are also generated using the same data set with the same geometry. The idea is that we design few aspects of motion in training data set so we can later validate them using our simulated results. So first, our deformable motion has a motion magnitude which randomized between 0 to 25 millimeters, where we also allocate different motions on each direction. Secondly, our motion pattern features a cosine temporal pattern with random frequency and random phase change, which is all under control. And thirdly, as we want to have a more consistent distribution across different cases, the spine regions were automatically detected and were excluded from our motion fields. So there's, as we can see here, there's minimum motion in our spine region. And finally, the motion vector fields are diffeomorphic in our training data set. So please take a look at our simulation results. On the left is a static reference, which is the input to our model as a condition. For each of the static reference, we run simulations on 10 different random perturbations, and we stratify, and for analysis purpose, we stratify our network generated simulations as well as our training data into 3 categories of mild, moderate, and severe motion. So here we show 3 motion simulation results from these different scales. And as we take a closer look at this motion region, we can see that different scales of motion have been introduced in these 3 samples. We can also see that motion is happening, for example, here, right, which demonstrates that our model is able to generate like a randomized motion distribution. To check the overall distribution of motion magnitudes, and we understand that 4-dimensional motion vector fields may be very hard to visualize across all the cases. So here we use the total distance travel as a metric, which we sum the distance traveled over all time points for every voxel in the image, and the maximum can be easily found. So here, as we overlay the total distance traveled map onto our image, we can clearly see that the motion are being generated at different scales as well as they are randomly distributed on the image. And then we want to compare between our training data and simulation data to see if our model was able to learn the underlying motion patterns which presented in the training data. So as we use the maximum of the total distance traveled, we can see that our simulation result actually agrees with what happens in the training data in terms of mild, moderate, and severe motions. We also check the motion frequency in our simulation. And here we use average speed of motion, which it computes the average of the distance traveled per time interval. And in our case, the time interval is the time between 2 consecutive partial angle reconstructions. Again, we divide the speed of motion into the low, medium, and the high ranges for analysis purpose. And it can be shown on the image top so that different speeds of motion are presented in our simulation results. It can also be seen from this plot that our simulation results agrees with our training data in general, although our simulation data are more biased toward the higher speed of motion. So we argue that higher speed of motion may be more obvious, can be more easier to pick up during the training. So our model is possibly favors to pick the higher speed of motion generation. And next, we check that the motion distribution on spine regions. So please recall that in our training data set, like the spine area was excluded from our motion field. So this area should maintain like a minimum motion. So there are 2 plots here actually shows the stats from our simulation data, which shows that our model actually have learned and produced that the spatial distribution that actually represent in our training data set. As you can see, the spine regions undergoing minimum motion in terms of total distance traveled as well as the average speed. Finally, diffeomorphism is also enforced in our simulation data. So let's first revisit these 3 images at different motion scales. Although relatively large motion were presented, like the diffeomorphism is still maintained. As we can see from here, there's no negative values of Jacobian determinants are presented. All right, so in summary, we presented a model based on generative adversarial networks that is capable of doing realistic stochastic motion simulation in Chromium CT data. We specially designed our loss objectives on cycle consistency, variety, and smoothness. As a proof of concept study, we demonstrate the feasibility of this model on highly controlled simulation cases, which yields consistent results with the trains presented in training data in terms of motion magnitude, motion speed, consistent spatial distribution, and diffeomorphism. For next steps, we will continue to explore the potential of this framework, and we plan to conduct experiments on controlled phantom and cadaver studies, which we will try to make the transitions to clinical data. And with that, thank you so much for your attention.
The paper is open for questions.
So, hello, great presentation. A question, have you compared your results to motion artifacts in CBCTs, in real CBCTs, or visual comparison?
Mm-hmm.
And maybe another question, so I would say that most of the motion artifacts are induced by respiration, and therefore why not use the deformation field from a 4D CT, for example, for generating this information for the simulation?
Okay, sure. So let me make sure if I understand your 2 questions right. All right. So first, you asked about like, have I compared our results with a real clinical or Chromium CT, right?
Mm-hmm.
So yeah, so actually that's something we plan to do, and these images have now been like visited by the clinicians yet. But actually, as you hear from our previous talk, right? So which was using motion composition. Just one way we hope to do in the next is that if I can use our motion simulated images and send to the motion composition branch, right, to see how that works, right? Mm-hmm. So that's for the first question. And for the second question, I think you mentioned about the respiratory motion, right, which you think can be better takes the advantage of using the 4D CT, right, 4D CT scans. So I think to answer that, I haven't think very deep into that. But for us, I think like in long-term goals, like we want to use to leverage the power of the learning-based methods, right? To actually extract the features from the real data. So which I believe, right, the 4D 4D real patient CTs can be a good option. Yeah. Okay. Thanks.
Okay. Thank you.
I have a follow-up question on this topic. So you're saying that you trust that the network will learn from the real data, the motion. It seems to me that what you're actually trying and very well doing is to reproduce the motion that you have input for the training. Mm-hmm. But this motion model is very simple for the time being. So I think that would be a good idea to indeed use real data to estimate motion and to input that to your simulator.
Oh, actually, like, yeah, thanks for pointing out. So I think like no matter what, the high level idea behind that, like at the very end of the day, we still want to apply the motion. Like we still want to get the motion from the real clinical, right, data. So although right now you see our motion, like in our training data is now so realistic, that's because right now we only want to demonstrate the feasibility of this approach that can do something, so we can gain confidence, right, to moving forward. to really using the real data. Yes.
Thanks. If there is no other question, let's thank the speaker again.